Welcome to the Programmer's Introduction to the Intel FPGA Deep Learning Acceleration or DLA Suite for FPGAs online training. My name is Carl. In this training, we'll cover the contents of the Intel FPGA DLA Suite and how deep learning inference tasks are accelerated on the FPGA. Here's the agenda for this training. We'll first discuss how FPGAs can fit in the machine learning solution overall. Then we'll look at the Intel FPGA DLA Suite contents, and lastly, we'll explore in detail how neural network inference tasks are accelerated on the FPGA and how the FPGA can be customized for performance. Intel has the best-in-class hardware portfolio for machine and deep learning, but software is critical to unleashing the full compute potential. To that end, Intel offers an optimized software stack in order to deliver game-changing AI applications. Intel is investing to fully integrate FPGAs in our full stack of software tools, including libraries, frameworks such as Caffe and TensorFlow, and tools like Deep Learning Deployment Toolkit and OpenVINO Toolkit. Intel's unified software ecosystem means you can use the same tools across Intel platforms, such as Xeon, Xeon Phi, VPUs, GPUs, and FPGAs. This enables not just hardware designers, but also software developers to take advantage of the capabilities Intel FPGAs have to offer. Let's just quickly go over the typical machine learning development flow. First, a starting network topology is chosen, such as ResNet or GoogleNet or some versions of it. Then, using a framework such as Caffe or TensorFlow, modifications to the network is done to achieve improvements. Next, you train the network. This entails starting with a large data set such as ImageNet or Kitty and using the training images to train the network weights. Once the network has been trained, it can be deployed. Is the main focus area for the FPGA, where it will now be fed new data or live video feed and perform real-time inferencing on it. As more data is collected and topologies can always be improved, or the training accuracy is improved with more reference images to handle more scenarios. There are many advantages of using FPGAs to solve machine learning inference challenges. Intel FPGAs are inherently designed for low latency, high throughput, power efficiency, and flexibility. And it's unique from CPU and GPUs in its ability to be customized based on these design pillars. When integrated into the Intel AI software solutions, platforms, and libraries, FPGAs are just as easy to deploy as other architectures. FPGA's custom hardware and flexible I/O and high on-chip throughput can implement low-latency data paths for deterministic execution. FPGAs are also customizable and reprogrammable, so it has the flexibility to accommodate latest neural network architectures. These characteristics, in combination with low latency, high throughput, and power efficiency, make FPGAs the accelerator of choice for inference. When you choose FPGAs for machine learning, you gain access to high-performance DSP blocks with hardened floating point and arbitrary precision fixed point support. This allows you to easily deploy lower precision networks, which can greatly increase performance. You also get distributed fine-grained DSP memory and logic, which keeps data on-chip, taking advantage of high on-chip bandwidth and low latency. With programmable fabric of the FPGA, you gain time to market advantage with future-proof solutions as Intel constantly updates the tools with the latest and greatest FPGA images. This also gives you the ability to support arbitrary architecture and various different use models, including multifunction acceleration. FPGAs can also take advantage of parallelism on-chip efficiently to provide deterministic low system latency. Because of FPGA's flexible I/Os and has great on-chip memory bandwidth, the total system latency, which equals I/O latency plus the compute latency, can be kept to a minimum. When you combine both the compute latency and the I/O latency, FPGAs often has much lower system latency compared to other solutions. Now that we understand why FPGAs can be used for machine learning inference tasks, let's take a look in detail at the contents of the Intel FPGA Deep Learning Acceleration Suite that can make it easy to perform these inference tasks on the FPGA. When processing data with deep neural networks during inference, there's typically three stages. First is pre-processing, where the data, for example an image, is formatted in a way that the network can understand. This can be resizing or cropping the image or changing the format from RGB interleaved to planar data. The second part is the actual neural network body. Here, the data is passed through, the various features are extracted by the many layers of the neural net. For image processing, typically we will use a COMNet, for example ResNet. For speech and translation, it may be some sort of a recurrent network. Lastly, the result of the network is post-processed for various purposes. For image classification, this can be a vector of tags and properties. It can also be indexed for object detection, localization, or segmentation. The Intel FPGA Deep Learning Acceleration Suite helps you process the neural net in the middle stages. Although you can easily add IP to the FPGA to do parts of pre-processing and post-processing as well, the Deep Learning Acceleration Suite is for neural net processing. The Intel FPGA Deep Learning Acceleration Suite is part of the Open Visual Inference and Neural Network Optimization, or OpenVINO toolkit. It's a comprehensive toolkit used for developing and deploying computer vision solutions on various Intel platforms. While this training focuses on the Deep Learning Deployment Toolkit, the OpenVINO toolkit also contains support for OpenCV, an open source library providing common infrastructure for computer vision applications that accelerate the use of machine perception on Intel CPUs and GPUs. The OpenVINO toolkit also implements OpenVX API, offering extensions and supports heterogeneous execution across accelerators. We're going to focus on the Deep Learning Deployment Toolkit, part of the OpenVINO toolkit. The DLDT is used to deploy trained deep learning networks through high-level C++ function calls. There are two components to the DLDT: the model optimizer, which converts and optimizes trained model on various deep learning frameworks and converts them to an intermediate representation, and the inference engine, the second part of DLDT, which is an execution engine that deploys the network by consuming the IR files through optimized C++ API. Deep Learning Deployment Toolkit can be targeted for many Intel hardware architectures, including FPGAs. When executing on the FPGA, the software layer, which is part of the DLA suite, is invoked, which programs the FPGA with bit streams and is built on top of the FPGA OpenCL platform. Here are the features of the Intel FPGA Deep Learning Acceleration, or DLA Suite, which is meant to accelerate inference of COMNETs. The Intel FPGA DLA Suite allows users to take advantage of the FPGA without going through the lengthy traditional FPGA development process. The DLA Suite consists of various implementations of the deep learning primitives organized in architectures of FPGA images that are tailored for different types of deep learning topologies, allowing users to implement various networks from LXNet to GoogleNet and a variety of other topologies without recompiling the FPGA. The DLA architectures implement optimized common deep learning primitives such as convolutions, fully connected layers, rectified linear units or ReLU, local response normalization, max and average pooling, concatenation, and many others. We're constantly adding primitives to DLAs as well. When executing the DLA library architectures, the data between the layers stay on the FPGA, and for very deep topologies, data just keep looping through using or bypassing the primitives that are needed for each layer. The diagram shows this particular architecture implementing CNN primitives on the FPGA in a sequence of convolution or fully connected ReLU LRN pooling layers. In the architecture, the networks are split into subgraphs, which are mapped iteratively to the sequence in FPGA for execution. Some primitives in that sequence are bypassable to support different combinations of subgraphs for the network. Finally, networks that use primitives beyond those implemented on the FPGA can be computed with a hybrid CPU-GPU FPGA solution. The various pre-built images can support many different types of network, including those listed here. Here's a high-level look at how the FPGA Deep Learning Acceleration Suite can be accessed from standard machine learning frameworks such as Caffe or TensorFlow using the OpenVINO toolkit and the Deep Learning Deployment toolkit. Trained models are first fed into the model optimizer. Here, standard framework file formats such as those from Caffe and TensorFlow are supported. The model optimizer in the Deep Learning Deployment toolkit will take the standard ML formats and converts it to Intel-specific intermediate representation. The model optimizer will also enhance the model for improved execution, storage, or transmission, performing various tasks such as quantization and model compression. The inference engine API in the DLDT will then take the intermediate representation and execute it on the various hardware platforms, which include CPU, GPU, vision processing units, or FPGAs. When the inference engine calls the DLA plugin for the FPGAs, the DLA runtime software layer is invoked, where the DLA graph API is used. Those API is then converted into execution on the FPGA, loaded with the various pieces of the DLA IP primitives, which can execute different layers of a deep learning network. The DLA suite comes with optimized turnkey binaries, which can be used for various networks, but the user can also create custom FPGA binaries with custom configured DLA IP loaded onto the FPGA for application-specific usage. The turnkey FPGA bitstream can natively support many ConvNet architectures, such as GoogleNet, ResNet, SqueezeNet, VGG, among others. As we said earlier, the DLA suite can be used in one of two ways. First, if you're a deep learning deployment software application developer, you will implement your software using the OpenVINO toolkit. You would choose the optimal turnkey solution from the bitstream library of many precompiled FPGA images, then run your application on the CPU and FPGA. All of your effort is focused on the software, and the FPGA just acts as an accelerator behind the scenes. If you're an FPGA architect, you can use the Intel FPGA DLA Suite and the Intel FPGA SDK for OpenCL to custom create a FPGA bitstream that suits your needs. Here, you can choose between primitives to include, as well as vectorization factor of the convolution processing engines. Or you can even write your own deep learning primitives using OpenCL, which are then synthesized and compiled into an FPGA image. The software application then will be able to access the custom bitstream using the same OpenVINO inference engine API. If you need to customize the FPGA architecture, the Intel FPGA DLA Suite allows you to select and place a custom collection of pre-optimized primitives and convolution PE arrays onto the FPGA. If there are primitives that you need but are not supported in the DLA Suite, for example, an uncommon activation function, then you can write custom OpenCL code for those functions and add it to the DLA crossbar through the DLA customization flow. The DLA supports two different types of custom primitives: unary operations, for example ReLU and hyperbolic tan activation functions, and binary operators, for example element-wise add or multiply. The custom-built primitives can be parameterized from a high-level deep learning framework, and with those parameters passed down to the FPGA layer through the OpenVINO software stack. There are currently two ways to use the Intel Deep Learning Acceleration Suite, with the acceleration stack in the data center and on edge computing devices. On the left is what the software and hardware stack will look like for deep learning inference execution on the FPGA-based Programmable Accelerator Card, or PAC, over PCIe in the data center. The Deep Learning Deployment Toolkit can be used over Intel Acceleration Stack for Xeon and FPGAs. At the top left, there is the User Deep Learning Inference application. The application is using the OpenVINO toolkit. The inference engine plugin will load the FPGA-based DLA runtime engine, which is built on top of the OpenCL framework, leveraging the acceleration stack, which is a collection of software, firmware, and tools which makes it easy to deploy Intel FPGAs for workload optimization in the data center. The DLA runtime engine interacts with the DLA workload on the FPGA, which contains the various deep learning primitives. The interface on the hardware side is handled by the Intel-generated FPGA Interface Manager containing pre-built IP using defined interfaces. On the right is the edge computing solution. Here the software stack is identical to the left, but at the bottom, instead of the acceleration stack, you have the OpenCL board support package driver. On the Vision Acceleration PCIe card with FPGAs, the interfaces to the CPU is pre-built as part of the FPGA OpenCL board support package. Again, the hardware is seamlessly hidden from the inference application in the OpenCL layers. As you can see, this suite of tools abstracts away the details of enabling the FPGA and allows software developers to easily leverage the FPGA for inference tasks. Now that we understand the Intel FPGA DLA Suite contents, let's dig deeper to see how the DLA architecture runs on the FPGA and how ConvNet's inferences are accelerated. The DLA architecture is built for performance and uses many different techniques to maximize parallel execution on the FPGA. We will discuss each of these techniques in depth in the coming up slides. Essentially, the execution of the DLA primitives are arranged in a subgraph that's most suitable for a particular type of network, and then repeatedly executed for each layer. The DLA suite comes with many different architecture designs for various different networks, so the optimal FPGA image must be selected prior to executing the DLA. And as we said earlier, users can also add custom primitives to the architecture. Before we dive deeper into the DLA architecture, let's first very quickly go over the compute involved in a convolutional layer of a CNN. In a ConvNet, there are many layers of convolution. Let's take a look at one particular layer. Every input feature map to the layer is a 3D tensor. In the very first layer, that would be the image. In the convolution layer, we would take a small filter, for example a 3x3 by input depth sized, and perform a dot product with the input receptive field, and produced a single output value. The output value is part of the output feature map of that layer. We will then slide the filter across and down the input feature map to produce a 2D output feature map. To generate multiple output channels, we will actually apply many different filters. Each filter is responsible for generating one output channel. Once the sliding dot product is calculated for each of the filters, the output feature map can become the input feature map of the next layer. And we will move on to the convolution for the next layer and repeat for all the convolution layers of a neural network. To illustrate how the layers are executed on the FPGA, we're going to use the LXNet as an example. Because LXNet is a well understood network and has relatively few layers, so it's easy to illustrate. The LXNet architecture consists of 5 convolution layers, followed by ReLU activation layers, and there are also 3 fully connected layers, followed by ReLU activations. There are also normalization and max pool layers following the first and second convolution, while another max pool follows the 5th convolution. As you recall, our DLA API is organized in a ring execution format. The feature map is stored in the stream buffer, and the various primitives, such as convolution processing engines, ReLU, LRN, and maxpool, are organized in a ring. To process the first convolution layer, the input image is read in from DDR and stored in the stream buffer. Then the data is processed through the convolution PE, ReLU, norm, and maxpool layers before being stored in the second buffer of the double stream buffer. When the second layer starts executing, the stream buffer inputs and outputs switch, so the output data of the previous layer is now fed to the convolution PEs. Again, in the second subgraph, we execute convolution, ReLU, LRN, and maxpool before storing the output feature map into the stream buffer. In the third subgraph of LXNet, we only compute the convolution and the ReLU activation, so the DLA configuration will set the LRN and maxpool blocks in the DLA to bypass mode. Again, the input and output of the stream buffer switch, and we process the third layer. We will continue the execution for the fourth layer. Again, LRN and maxpool are bypassed, and the stream buffer input and output swap. For the fifth convolution layer, the LRN is still set to bypass, but the maxpool is again enabled, and the stream buffer data is again processed. For the sixth subgraph in LXNet, it's a fully connected layer. In the DLA, fully connected layers use the same processing elements as convolutions, since the basic operation of the dot product remain the same. However, we need to configure the PE to be in the fully connected mode. Here, we also have a ReLU layer, but bypassing norm and pooling. For the seventh layer, another fully connected layer, the subgraph is executed the same as in the previous layer. For the final fully connected layer, the ReLU, norm, and maxpool are all disabled. Now that we understand how subgraphs are executed, let's look at the convolution processing element, or PE, in more detail. The DLA convolution processing is made out of an array of processing elements. The DLA can run all the PEs in parallel, with each PE executing a different filter from the same convolution layer. The input feature map is sent to each of the filter PEs in a systolic array format. The parallelism here is referred to as K-vectorization. The second type of parallelization the DLA execution engine can leverage is input depth parallelism. Parallelism can be achieved across the depth of an input feature map because each processing element is made to handle a vectored operation across a certain amount of depth. The parallelism here is C, or channel vectorization. Lastly, when given the amount of resources in the FPGA bit streams the DLA provides, there's a trade-off between the number of primitives supported, the data type, and the C or K vectorization. The bigger the C and K vectorization factors, the more computational bandwidth an FPGA architecture will have. Another technique that DLA will leverage to increase performance is Winograd Transformation. For certain data types, Winograd Transformation can perform more convolutions with fewer multiplications, and this will allow higher throughput on the FPGA. Take a 6-element feature vector, which needs to be convolved with a 3-element filter. Performing a standard convolution with the sliding filter on the 6 inputs will require 12 multiplies. With the Winograd transformation, we can take advantage of filter use, perform a data transform, and we'll be able to perform the same convolution with only 6 multiplies. This will essentially double FPGA throughput given the fixed number of hardened multiplies on the FPGA. The transform itself is done as data is streamed out of and into the stream buffer. When performing fully connected dot product computation, the processing elements will not be able to reuse the filter weights, since in the fully connected layer, each filter coefficient is only used once as there is no sliding. This characteristic is different from convolutions and will result in a very memory bandwidth intensive operation. The solution DLA uses to gain more efficient use of the weights is through batching. With batching, multiple images are processed in parallel. In the convolution layers, the images are processed sequentially, but during fully connected layer, feature maps from multiple images are loaded into the on-chip buffer together, then calculated in a pipeline fashion in the processing element for maximum total throughput. The on-chip feature cache built on the FPGA is a double buffer stream buffer. The buffer can be populated from on-chip sources as well as processing primitives. And as the data streams out, it is sent to the various filter processing elements in a daisy chain manner. The stream buffer is double buffered, meaning as data is flowing out of the input buffer, the data after processing comes back and is stored in the output buffer. This allows the convolution to overlap with cache updates. And as we move from one subgraph or convolution layer to the next, the output of one layer becomes the input of another. We simply switch the designation of input and output buffers. This process eliminates unnecessary external memory access and takes advantage of the very high on-chip memory bandwidth of FPGAs. The filter cache in each processing element is designed to store filter coefficients during convolution. This cache is also buffered, so when we perform convolution for one filter to calculate output feature map, the next filter from the same convolution layer is being prefetched. This again eliminates any overhead in accessing filter coefficients. During the fully connected layers, the filter cache is actually used for batched feature data, while the mainstream buffer is used for the fully connected layer coefficients. To support various data types and various different primitives that are used in different neural networks, the Intel Distribution of OpenVINO, which includes the DLDT and the DLA Suite, ships with many different FPGA images that's optimized for different boards, different data types, and architectures. Ensure to find the optimal FPGA image for the network and data type you plan to run. The name of the bitstream starts with the version of the DLA, then there's the board. RC is the designated board name for ARIA 10 pack cards. This is followed by the data type and then supported topologies or bitstream features. To understand the features and capabilities of each FPGA bitstream, check the link documentation. Remember, you can always create custom FPGA images based on need. With the different architectures in mind, it's important to choose the optimal FPGA image because there's a trade-off between feature support and performance. If you use a generic FPGA image that can support many different types of primitives, as on the right, then you'll have less space left for the convolution PE arrays. Whereas on the left, choose the image with only the primitives you need, and you'll have much bigger size left for both the convolution PE array as well as the feature map stream buffer. This will result in much higher performance. Here's the current list of the primitives DLA architectures can support to run on FPGAs, as well as the list of tested neural network topologies that can be accelerated on FPGA boards. Not every FPGA image shipped has all of the primitives, so just find the image that best matches your network, again using the documentation for reference. Using OpenCL, you can always add primitives to custom FPGA images. Keep in mind also the list of supported primitives and topologies are constantly changing, and check the DLA documentation and OpenVINO documentation for the latest supported primitives. Another thing to keep in mind when choosing a network architecture FPGA image is the data type. With reduced precision, you can perform more convolutions in parallel, and this is a significant trade-off between performance and accuracy. Keep in mind the default DLA data types are all reduced precision floating point types ranging from FP32 down to FP8. When executing the reduced precision floating point numbers, FP16 and lower, the DLA will perform block normalization, meaning normalize the exponent for all values, and then instead of performing floating point multiplies, it will use fixed point multiplies. With FP32, we can only perform one multiply at a time per DSP block on the FPGA. But with FP16, we will be able to do 2 per DSP block using 18 by 18 multiplies. And with FP11, we will be able to perform 4 multiplies at a time using a single DSP block. so the amount of computation performed scales really well. Another benefit of using reduced bit floating point numbers is that unlike int 8 or 9, there's no need to retrain the network. Just quantize down from the standard FP32 and it'll achieve better performance with less accuracy loss. This concludes the training. To summarize, FPGAs provide a flexible, deterministic, low latency, high throughput, and energy efficient solution for accelerating deep neural net inference applications. The Intel FPGA DLA Suite allows you to quickly accelerate these inference tasks on the FPGA without writing RTL blocks. The FPGA for deep learning inference can be accessed through the OpenVINO Toolkit, which allows a single application to access multiple deep learning frameworks as well as multiple hardware accelerators. Lastly, the first version of DLA Suite is available for PCIe-based Intel Programmable Acceleration Card in the data center. Here are some additional references. To see more detail about how to run inference tasks, please view the follow-on online training, Deploying Intel FPGAs for Deep Learning Inference with OpenVINO Toolkit. I've also provided links here for the main Intel AI portal and the OpenVINO Toolkit, as well as more information on Intel FPGA used for AI, as well as the acceleration stack which can be used with the PAC board. One last thing, when you register for this course, a link was sent to you in your confirmation email that links to a short online survey. Please complete the survey to let us know what you think of this training and how it might be improved. Thank you very much for attending the Introduction to Intel FPGA Deep Learning Acceleration Suite training. Best of luck with all of your designs.